There, guys. Well, we have got to the last unit in the book, Exciting Times. This one is all about graph theory. So let's have a little look. It's called Optimizing Complex Networks and Graph Theory. So graph theory. This is not the type of graphs that you're used to in statistics. This is not about scatter graphs and histograms and box and whisker plots or whatever. This is about vertices and edges and networks, and some algorithms will turn up here as well. This, in fact, will be quite a tonic, like a good bit of fun compared to that lengthy chapter 14, which was all about statistical tests. Okay, so let's have a look at where they're starting here. So they talk about vertices, of course, are the points. They talk about edges. They talk about weighted graphs. So if there are lengths on each of the sides, there could be lengths or they could be costs of doing something rather along that pathway. So these numbers on the sides mean that we would have a weighted graph. You do not have to have a weighted graph, in fact. You can also have directed graphs. So you could have particular directions going in one direction or another direction, or potentially going in both directions. We could have two pathways there. That would be examples of weakly or strongly connected graphs, but in this case, we can go in any direction because there are no arrows in this case. Now, a classic example of an early graph is, let's have a look at the London Tube map. London Tube map. Okay, and something like this. This is, I can't remember when it came about, like 1920s or something or other. So this is your classic early graph, and of course, in this case, your distances are not being represented in the map. On the map now, potentially you could put lengths on here, so numbers on here. So potentially this one has actually got some numbers. Here we go. The real distances between stations, and here we're seeing we've got some real distances put on this one in a weighted graph, but it is not geographically correct. Okay, right. They also talk about the Koenigsberg bridge problem, which is this one. There we go. There's the Koenigsberg bridge problem. I was just doing it over here, and I messed up a little bit, so I restarted. But the idea here is that you start, maybe you start on this side, you start here, and you've got to cross all of the bridges, and only once, and that you should end up potentially somewhere else, or potentially at the start if you really possibly can. So this is a simple little puzzle that you can try out, and I was just showing that if you put a dot on each of these islands here, then you can kind of create, let's just go with two bridges there, you can create a kind of network here as well. So there we go, there's our network in this case. Okay, that's the graph as made with vertices and edges in this case. Okay, now that turns up later. We'll look at that with Eulerian trails and Eulerian circuits later on. I've got to be careful with the terminology because there are things as circuits, trails, paths, cycles, walks. They all mean something slightly different. So the terminology matters, and that's just what we're going to look at to start off with. So, okay, so let's shift on here. Kind of interestingly as well, this is now in Kaliningrad. This is kind of interesting, just a little extra, okay? If you look at Kaliningrad, it's here. It's right next to Poland, and it's in Russia. But if you have a look, Russia is extremely small. So this is not an often talked about part of Russia. It is separated from the rest of Russia, which you can see over here. Okay, so it's kind of interesting. Yeah, so it used to be part of Germany, in fact, which was called, which is why it was called Koenigsberg. Okay, King's Hill, I think. Okay, so let's have a look at this. So walk is so what's a walk? Walk is a sequence of vertices passed through when moving along the edges of a graph. Okay, and then we're going to talk about adjacency tables. So This is an adjacency table. It shows you where we have connections between things. So if we start at A, we can get to C. Now this is normally where we start. This is where we can end up. And in this case, because we have symmetry, that means to say that we don't have a weakly connected graph. We can go in either direction. So we'll see a bit more of that when we go through this one. Now, a walk could be to say, let's go from A to B to D to B to C. You can repeat vertices, you can repeat edges. Walks are doing what you want. They're doing what you like, but you can just name them. I'm going A to B to D to B to C. You can name them by their vertices. Okay, so let's ditch this. Let's put that one in the bin. And let's just get rid of this. So we've got the adjacency table in this case, which we can turn into a matrix as well, which we will do later on, in fact. And so this question says, the table shows the connections between the stations on a small mountain railway. An empty cell indicates no direct connections between the stations. Show this information on a graph, and you can probably see it over there. So let's just hide that one up. So how are we going to do this? Well, let's say we've got A. Let's start with A. A is connected to B and C. Okay, I'm just putting these anywhere I feel like. So it's connected to B and C. I can see that. I can see that C is connected to B as well. B and C are connected. So B is connected to A and C. B is connected to A and C. That's true. C is connected to A, B, and also D. So here we go. Here's D. D is only connected to C. So there we go. There's my graph. Okay, that's done. You can see that we've got, like I said, we've got symmetry down the diagonal there. So for example, this one and this one, that's to say that A can lead you to C, but also C can lead you to A. So it's strongly connected. So you could say that there's a route in this direction and a route in this direction as well. But frankly, if we've not got a directed graph in this case, we don't need to worry about that. Okay, so let's bin that. Let's take this, let's bin it. Let's just have a look at example 2. Okay, so example 2 is saying the table shows costs in dollars of traveling by bus between stations. Okay, right, so there we go. Let me just put that in the bin as well. That's from A. Was building it up. So we've got the cost in dollars per stations. Again, we can see that we've got symmetry down this line here as well. So it costs the same going in one direction as it does in the other direction as well. Hi there, Bella. Just doing a quick video here. Okay, so you're laughing at me now. Okay, right. So if we have a look at this, we're going to try and show this information on a graph. So obviously we're going to make that graph to start off with. So we've got point A to start off with is connected to B, C, and D. So we can go B, C, and D here. Okay, so there we go, B, C, and D. And we can put the lengths on there already. We've got 4, and we've got 7, and we've got 6. And B leads to both A and C. So B also connects to C there with a length of 5. And to be honest, we only really need to figure out the ones on this side because we can see we've got symmetry here. So all of these are just sort of copies of the ones on the other side. So with C, we've now got 2 extra connections to D and E. So D connects there with a length of 3, and E connects. So let's put E over here. And you might have to draw this out twice to make it slightly neater. And then so C connects to E with a length of 6. You don't have to worry about the size lengths being okay. The weight tells us the length of this thing. And then D connects to A, C, and E. So A, C, and E. So we're missing here the connection to E. And that has a length of 2. And then finally, we have E is connected to both of these two, but we don't need to worry about that side. So we are done with that graph. Now you can see that there are many ways of doing this, and they're all valid. So here's some other ways of doing it. And you might want to rejig that I mean, what I've done there is fine for exam purposes, by the way, but you might want to make it neater if it's totally scruffy and illegible. Okay, right, so then that's 15A. So let's have a little look at 15B as well. So 15B is now talking about directed graphs. So let's have a look at this. What have we got for this? We've got, let's go this way. So a few notes for this one. So for connected graphs, connected graph, it is possible to construct a walk between any two vertices. Connected graphs. Okay. So a connected graph means to say, look, I'm going to need something to connect this whole thing up. So there are no, so it's possible to construct a walk between any two vertices. So, if I put that measured length in, I can now get from D to C, for example. So if it's not connected, it might be that you have some subgraphs in here. It might be subgraphs of a larger one. If I put these two lines in here, then this here is a subgraph of that entire system. But a subgraph of a graph G consists entirely of vertices and edges that are also in G. So, you just take a few of your vertices and come up with some of your edges, and that will give you a subgraph. In this case, this one is made up of two connected subgraphs. What are we talking about here? No, they're talking about this example. The graph here is an example of an unconnected graph. It's unconnected because no walk exists between A and D. It is, however, made up of two connected subgraphs. There we go. There's a couple of subgraphs there which are connected themselves. Okay, we've talked about directed graphs. So directed graphs just have, let's just chuck this. So directed graphs just have some directions on particular edges. So let's have a little look at this one here. And we can see that this one is weakly connected because you cannot go back and forth between, for example, D and C. You can only go from C to D. Okay, and sometimes if we could say that, for example, A and B are strongly connected in this situation. Okay, right, and then they talk about the degree of edges. I think we mentioned this potentially. So this has a degree of 3, this has a degree of 2, this has a degree of 4. It's about the number of edges coming into that point or leaving that point equivalently. Okay, so for example, F has degree 2. Okay, there are 2 edges coming out from that point. You can also talk about the in degree, and you can talk about the out degree as well. So if we have a look at this, the in degree of A is 1, but the out degree of A is 2, for example, because you have 2 edges leading out from that. Okay, so that's probably enough at the moment. And so there's 15A and 15B, which you can have a go at. And then there's a little bit more theory for C and D, coming up with more matrices, in fact, coming up with matrices for unweighted graphs. And then for, let's have a look at C. Yeah, still all unweighted graphs for C and D. Okay, thanks for listening.